Okay, let's start with the last lecture by all the award winners for Lifetime Award. Leslie Valiant. So Leslie has been in computer science for over 50 years by now, I assume, and graduated from Cambridge. He's my dear colleague in Harvard for many years. I came after Leslie was there. We are neighbors, so we talk a lot, and I always admire his originality and his courage on tackling the most difficult problem in computer complexity and learning freely. He has set a really good model for all us to learn. I think artificial intelligence and all these new subjects are influenced by his foundational work. It was explained on Sunday. I will not go about it again, but I think he's a great man. Let's have let's.
Thank you. Well, thank you very much for the introduction. So I've enjoyed having Professor Yao as my colleague for several decades at Harvard. I've obviously admired him for his mathematical work. And as far as this ICBS occasion, I have to mention that as a promoter of mathematics, Professor Yao is absolutely unique in his vision of mathematics being so broad, inclusive, and yet of exquisite taste. So it's a unique combination, and I think occasions like this are a result of his efforts and his nature. So what I want to talk about is a topic on which I've worked for a very long time, and various parts have come together recently, and it's become a book whose title is roughly my title. So this book is written for a general audience so that people aren't frightened away, but the actual book, if you follow through the footnotes, endnotes, references, there's a technical proposal there. Also, from the book, it's not its main purpose. One can read off an interpretation of current AI, which is different from the conventional one. But this is kind of wasn't the main purpose of the book. So the goal of the book is really to understand ourselves as humans. So the topic is really about humans. Okay, so says as many talks in computer science start with a quotation from Alan Turing. And so he asked in a radio broadcast, can every task done by humans be done by a machine? And so I'll just quote. So he said, it's customary in a talk or article on this subject to offer a grain of comfort in the form of a statement that some particularly human characteristic could never be imitated by a machine. It might, for instance, be said that no machine could write good English, or that it could not be influenced by sex appeal or smoke a pipe. I cannot offer any such comfort, for I believe that no such bounds can be set. Now, the important point about this, several important points. So one is, of course, that people still ask the same old question. But my recommendation is that we take Turing totally seriously, because this wasn't just some idle philosophical comment, but this was really based on his main science. So his main science was what became known as the Church-Turing thesis, that what we understand as computation is really universal for all ways in the physical world in which we can do mechanical information processing. And although there are many comments one can make on this statement, I would suggest that it's not very productive to try to disagree with Turing. There are much more productive directions to go in. And in particular, my theme is that, okay, if Turing says that basically what humans can do and machines can do are the same, then what's left to investigate? Well, what's left to investigate is to define what either machines or humans actually do. And I think largely unsettled science is to characterize what are human capabilities. What is it that we do what is it that we want our machines to do. And to my mind, it's amazing that we don't understand ourselves too well. So in particular, we may think of ourselves as being intelligent as a species. And so this is maybe how we self-identify as a species. In fact, we seem to be obsessed with this notion of intelligence. So when we measure our mental abilities, we call the result an intelligence quotient. When we attempt to emulate our mental faculties, we call it artificial intelligence. Some fear that machines more intelligent than humans could be an existential threat. And in searching the cosmos, we're seeking intelligent life. So you would think that we understand what intelligence is, but in fact, even when experts get together, it turns out that they don't. So famously, the American Psychological Association, who are responsible or felt responsible for what's going on with IQ tests, finally wanted to figure out what is intelligence. And one of the quotations from their famous report is that when 24 prominent theorists were recently asked to define intelligence, they gave 24 somewhat different definitions. So intelligence is not a very good notion. So historically, this is not mysterious. So Spearman, whose work really inspired IQ tests, defined intelligence as statistically, indirectly. It's some kind of correlation. It's not an explicit definition of how you recognize an intelligent person. So we don't have an algorithm for. We think we recognize when someone's intelligent, but how do we do it? There's no definition. So in some sense, what my notion of educability is about is trying to define some notion which is definable and which may be more useful than this notion of intelligence, which no one can define. And for example, I don't think the term intelligence has been useful at all in the development of AI. So I think the word learning has been much more useful because then we try to understand what learning means. So, so Turing gave us a license to discuss humans and machines in the same breath. And this is roughly what my proposal is. But the question is, how do we phrase the question? So, so this is the cover of the book, minus the author and the title. And I just want to acknowledge the cover designer who summarized the meaning of the book by having this prehistoric arrowhead and a picture of a computer cursor and asking how did humans get from one to the other? So in particular, the question asked in the book is, what is the cognitive capability that enabled humans to go from the Stone Age axe, Stone Age arrow to computers? And okay, so one can call it the civilization enabler. It's some cognitive capability. And almost certainly the change isn't something biological. I mean, no one thinks that some biological change swept through the human population in a period of a few thousand years. And in fact, probably even in the 300,000 years, which is believed to be the age of our species. So there are several things to say about how this question is phrased. So for example, this gives one a license to ignore phenomena which are more ancient than human. So certainly vision, locomotion, emotions are all pervasive in the animal kingdom. We share it with other species. This is not what separates us from other species. And so what separates us is more like some disembodied computation, because the way we interact with the world is most of it has got a much more ancient heritage. So the methodology I use is that of computer science, and very simply, the notions are that we want to deal with functions which are well defined. So this is just mathematical functions. So input-output functions. So if you claim that some organism exhibits some behavior, then you should specify in what way the situation before the behavior is different from the situation after, so it's just mathematical functions. And the second insistence is that every function you suggest should in principle be computationally feasible. It shouldn't be a pie-in-the-sky dream. Okay. So this approach is based on advances in computer science in recent decades. So the prediction that we should do psychology through computational models is implicit in Turing, of course, but Herbert Simon, for example, predicted that within 10 years of 1958, models published in psychology journals would be computational. So this didn't happen, and part of the result was that the use of computational models needed is slightly more advanced than what was available then. Okay, so what is this civilization enabler? So of course, in some sense, this question has been asked many times. So for example, there are academic studies of any number of ways in which humans and their nearest relatives differ. There's one website where you can look up academic literature on 617 different topics. But we're asking for something a bit more specialized. We're looking for cognitive capability that's special to humans, and the one that enables humans to achieve the civilization we have. So we're not interested in just any difference between humans and other species. So for example, people claim that eyebrows are unique to humans, but there's no theory that if you have eyebrows, then you can go to the moon. Animal domestication, so there are many things important in human history which may have been crucial, but again, just because you can domesticate animals doesn't explain how humans do the things we do in advanced technology. There's biological things where we're a bit different. So some people emphasize that humans collaborate a lot. Well, again, by itself, it doesn't explain everything, and many other animals do it. Social learning, so we learn from each other. Intelligence, as I said, that's rather badly defined. So symbols, language, so this must get closer. But again, these aren't cognitive capabilities which by themselves explain how we can develop a technological civilization. If you teach an ape language, it doesn't change its behavior. Okay, so is this an overambitious goal? Well, just 3 comments. So we're trying to capture a fairly short period of evolution, how humans are different from our predecessors. So what did Darwin say about this question? Obviously, he was concerned about this. So basically, his answer was that if you enumerate all the usual candidates for in what way humans are different from other animals, he said that we're different in degree, that you can't isolate a single dimension in which explains our success as a species. And so after all this previous investigation, what advantage do we have now to investigate it? Well, I think it's very simple. The point is that the many other communities who investigate this question have usually used what in this room we'd use are rather vague words, okay? And if you combine the vague words, then the notions get even vaguer. So but by being more precise, main idea is that we can suggest more complex hypotheses. So maybe the answer to this question of what is this civilization enabler may be just slightly more complex than these phrases I put up there. And by using more precise language of mathematics, you can attempt to isolate notions which are just complex enough to answer this question. Whereas if you don't formalize at all, then you just can't. So what I want to do now is to actually tell you what my proposal is for this civilization enabler, and then at the end I'll give 6 different directions in which, if one takes this proposal seriously, then it's got consequences which are of interest to me. So these would be 6 directions in which I've been driven to think, which I wasn't driven to think before. Okay, so what is this proposed civilization enabler? So it's defined computationally, and it is a composite of basically 3 different things in some context. And the name I've called this composite concept is educability, because that's the notion of education is what it reminds me most of. But this is a kind of a technical definition where this is the given name. So it consists of 3 capabilities in a context. So the first capability is to acquire beliefs, knowledge, whatever, by generalizing from experience. So this will be formalized exactly as standard machine learning is formalized and practiced today. So the fact that machine learning has some successes is some support that one can get started. Okay, so the formalization of this, I'll give all this in slightly more detail, but this is just standard machine learning, if you like. But that's not enough. So the second part is that if we've learned various things, various beliefs, then we should surely be able to apply it in combination to specific situations. So this is like chaining together 2 beliefs you have. It's a very simple form of reasoning, where you apply things you know in a new combination. And you do this prompted by a particular situation. So you want to make a prediction about a particular situation. So this is a view of reasoning. And then the third part is that humans can also acquire beliefs, knowledge, by having it explicitly described to us by others. So I can acquire a belief by having my own experiences, seeing examples, but I can also go to a lecture and learn someone else's conclusions about what they've learned from the examples. So this is how science works. So I can go to a course in, say, quantum mechanics, and I learn lots of theories which I certainly can't have deduced from my experiences, because they were deduced from experiments done with great effort by others. But I am able to internalize formulae. Sometimes people give me instructions, recipes, rather readily. And this is a part which other species have limited capabilities. And all these are integrated. But you have to say something about the context, because if you can do these 3 things in some very trivial context, like a world in which there's, say, 1 pixel, then that's not very useful. So I'll explain all this. So all this knowledge has to be relevant or to scenes with multiple objects. So we can analyze a scene. I can talk to 3 people. I can see who's sitting next to whom. So it's being able to analyze restricted scenes with several objects and relations is important. And also I can dream up symbolic naming, which means that I can arbitrarily name things and refer to them. Okay, so very briefly, in educational philosophy, people discuss things which are related to all these things. So number 3 is learning by someone lecturing to you. Number 1 is more hands-on learning from experience. And number 2 is being able to apply what you've learned to particular cases, possibly by reasoning on what you've learned. Okay, so I suppose in mathematics education, all these 3 things are reflected. So number 3 is learning the theory. Number 1 is examples. And number 2 is number 1 is examples of concepts. Number 2 is doing exercises where you try to apply what you know. So okay, so I don't have to speculate how these 3 things we acquire through evolution, but for a moment I just will. That it's possible to make some plausible timeline. So just basic learning from experience, adaptation, that's clearly very ancient. the most primitive animals had that, and once they had that, then they could surely also combine them. So the third part is the most recent acquisition, where we can take instructions from someone else and kind of execute them. So one plausible hypothesis would be that we acquired this perhaps in one of our predecessor species. So our own species apparently is about 300,000 years old. I suspect our basic capability for these three things combined in the appropriate way is very ancient. It's probably been with us from the beginning as a species, but it's just taken a long, long time to get rolling like a snowball rolling, because this aspect of exchanging knowledge only gains you a lot if you have lots of knowledge to exchange. Okay, so just to explain in slightly more detail what these three parts of the proposal are. So one is generalization from experience. This is exactly what I'd call standard machine learning, where you've got a learning algorithm. Deep learning is an example. You're given some training examples with their labels. You're given pictures labeled whether they show an elephant or not. And what this algorithm produces is another algorithm called the classifier. And then the classifier, given a new example, which is not labeled according to the category, whether it's an elephant or not, this classifier will tell you whether it's an example or not. So this is learning by example. But one has to formalize this a bit more. And certainly one important fact, which theoreticians and practitioners know, is that this only makes sense if you specify a world in which the learning happens. So D would be a source of data or a probability distribution. And the magic of machine learning, of course, happens when the examples come from from the same world as where you're going to test them. Okay, so if you learned a lot, but you go to a different planet, it may not be useful. So one needs to formalize this. So the formulation I use is the probably approximately correct model of learning, which basically the main quantitative requirement is that by making more effort in the learning, so computational effort here is both processing examples, but the totality is the computational cost, how many computational steps you make in deducing the classifier. You want the prediction error to decrease with more effort, but you also want it to decrease fast enough that you're well rewarded. So in particular, the requirement is that this be some algebraic law. So the more effort you make, the better you're rewarded. And in particular, what an algebraic law says is that supposing with 10 times more effort, you halve your error, then if you make 10 times more effort still, then you want to halve the error again. So for certain theoretical learning algorithms which can be analyzed, one can demonstrate this property. And empirically for heuristics, which are widely used, when these methods work, they exhibit this property. So the reason why AI companies spend such enormous amounts of money on training is that they find that however much money they spend, if they spend 10 times as much money, they get rewarded a little bit more. And this is like a drug on which it's hard to get them off. Okay. Now the importance of having a mathematical model of what you're doing is several, but I'll just illustrate one thing which I think is relevant, which I've only recently fully appreciated. So the way I've sketched the definition of back learning is that it's about generalization. If you've seen examples, how do you predict some new examples? So it's about generalization. Now, if you took a less formal view of machine learning, then you think of humans and all our capabilities, and so this is a list of things which people complain that machine learning algorithms can't do. So generalization they can do, but people say, why don't they explain what they're doing, etc., etc. So the last thing I'll say something more at the end, out of distribution means that sometimes we can make, humans can make predictions about situations which don't look like your previous experiences. So how does that happen? Okay, so the fact that current machine learning doesn't do everything people wish is a suggestion that obviously we have to do something else beyond this learning by example. But I think the important thing to note is that the learning algorithms which are widely used are the winners after decades of competition among different learning algorithms just for this task of generalization. So, present machine learning, this back learning model, and this practical implementation of it, it's all been focused on generalization, not on the others. So, for example, large language models are trained to predict the next token, and they're very good at that. What else you can rely on them to do, I suppose no one knows, and this is what people are trying to investigate, but maybe they're not good at any of the others. There's no reason to believe that they're good at anything else besides predicting the next token. So predicting the next token seems to imply very smooth language. So it's certainly they produce very smoothly flowing natural language, which is very impressive. But the question is whether you should listen to the words is a different question. Okay. So just one comment which goes a bit back to the practice of AI and maybe addresses some of the issues discussed yesterday. So the reason that that machine learning algorithms are hard to understand or how they work in particular cases is no mystery. So the practical algorithms currently used, like neural nets, so the main point is that they can represent functions which no one believes are learnable. So, for example, they can represent functions that can be used for cryptographic encoding, which are conjectured to require exponential time to learn. Okay, so the practical learning algorithms are heuristic, which work some of the time. So we already know this, that they work for only certain data sets. They happen to work for important data sets, but just because they work in a setting where many things are not learnable, suggests that it's very hard to figure out exactly which data sets are good and which data sets are bad. So the mystery of why a data set is good for deep learning, the mystery is almost in the data set itself. And the fact that we can't identify what's special about natural data sets is the real problem. And furthermore, that basically in all of computer science, we are in a similar situation, that heuristics are used all the time when we don't understand exactly why they work, but that's fine. So I think for learning, so the fact that given a data source, we can certainly test whether a learning algorithm has succeeded, but just testing it on more examples is the rational reason for relying on them. And worrying more about what we don't understand about it isn't very productive because it's kind of what you'd expect. Anyway, that's just a side remark. Okay, so let's now go back to the main theme. So the main theme is that we're trying to explain what this notion of educability is, and the first part was standard machine learning. So the second part is a notion of reasoning on what you've learned, and here the main difficulty is that when we learn, our beliefs are uncertain. It's different from standard logic, and so here I use a formulation which I came up with some time ago called robust logic, and the goal of this is to mimic standard logic in that what you really want to achieve is that when you chain together two beliefs, you want some reason to believe the conclusion. Okay, and this is called soundness in standard logic, but here we'll have to redefine it. And everything we want to be computationally feasible. So basically what this will boil down to is that we will, instead of having one big, let's call it a supervised learning box, we're imagining this in a human context now. So that's one idea of what we are, a big learning box. So here I'm saying that probably doesn't quite work. What we really are is many boxes. And so, for example, we could have a separate learning box for learning each word of your language. Okay, and oops. How do we do this? Okay, and just to emphasize what we're trying to do, that is not quite trivial. So there's a quotation attributed to Winston Churchill that true genius resides in the capacity for evaluation of uncertain, hazardous, and conflicting information. I'm using this quotation in a slightly ironic sense because it's not only geniuses who need to do this. So the lowest animals also live in an uncertain, hazardous world, and all the time have to resolve uncertain information which they've learned. So this is some very basic capability which we need to have some view of. So for a single learning box, we have the standard notions of generalization. So what we want with this robust logic is to have the same, but also have some soundness guarantees when you chain together two beliefs. Okay, and very basically, what you hope for is that if you've got two beliefs which are supported by your data to 99% accuracy, then when you chain them together, you want some lower bound on how much you should rely on it. And maybe it's 98%. Okay, so you want some principles for believing in your chaining. Okay, and this, as I said, this has to be in a rich enough world. So this is a crow doing some difficult cognitive task where it's got some bottle and some water and wants to get a seed from the surface of the water and it figures out how to pour some more water in the glass. And the point here is that that the information which this crow is faced with, you have to put it in the crow has to understand. So this will consist of separate objects. There's a seed, there's water, there's a glass, there's a water level with some relations. And this all has to be understood by the crow. And further on, unlike standard machine learning examples, in real life, when we learn from cases with very partial information. So when this crow sees the situation, it sees the glass, it sees this and that, but most of the other things in this environment are unsaid. Okay, so this is the context, and just a quick illustration. So how this mind's eye works is that at any moment, these blue circles represent a token which can take on which can be described by some set of predicates or relations. So you may be thinking of your dog, and you may be thinking of a second object which your dog likes, and you conclude from your knowledge in your brain that it must be a bone which your dog likes. Now, instead of standard logic, in this robust logic, the rule which you invoke to deduce bone will be a learned classifier. Okay, so you will have learned some expression from a learnable class. So this could be a deep neural net, and this would be a deep neural net whose output is bone or not bone. Okay, but actually, one important consequence is that in machine learning we learn approximate equivalences rather than logical implications. So in machine learning, you have to be right both ways. But these you can still chain together. And the idea is that in your mind's eye, you have a situation described like a dog likes, and then you'll use the learned knowledge in your brain to fill up the diagram and make predictions which presumably will be true about the world. Okay, so just one comment. So humans can answer questions like, did Plato own a cell phone? Although in the evidence you've been given in your life, you didn't have many examples of Greek philosophers with their domestic appliance, for example. Okay, so how do we do it? So we do it by presumably training together some facts we know, which we know independently, which we will have learned. So one thing which robust logic does supply is a principled way in which you can do this kind of reasoning. Okay. Okay. So and then there are some theorems about this. Okay, but again, let's go back to the civilization enabler. And this so third part was being able to take instruction from others, but all in this richer context I've described. And this is basically the capability of receiving an explicitly described program or instructions, recipes, a formula, and like a universal Turing machine, being able to evaluate them. Okay, and so I'm saying educability is the realization and integration of these three capabilities. And going back to the last thing, so the clear upside is that obviously being able to take complicated instructions from others, like going to a lecture course, has this enormous advantage that discoveries made with painful and costly experience can be shared very efficiently. There's no chance that we could have discovered all of science if we couldn't share knowledge. Also important, I think, is that some of the discoveries are very general, like new methods of reasoning, like arithmetic, needed to be discovered before we could do any kind of quantitative science, and the spreading of such simple new methods of reasoning are very important to the development of civilization. So accumulation of science enables us to do all kinds of things, but also complex cultures. Okay, so just summarizing this with a diagram. What I'm saying is that biological entities live in a complex environment. So basic pack learning and robust logic are somehow grounded in this environment, because what basic machine learning does is that it learns from the environment to predict the same environment. Okay, so when a snail learns about its life, where to find food, it's got examples of good behaviors, and assuming the world doesn't change, it's safe. It's adapted to the real world. But this third part of this educability framework, where we receive programs from other people, that's something new and different, because it is not grounded. So if someone gives you a recipe for cooking or a formula in quantum mechanics, who knows whether it's true? It could be false. They could be lying to you. And in general, it's very hard to test. Okay, it doesn't come with a guarantee that it's tied to the world. I'll say something about this in a second. But the point of basic machine learning and robust logic is that these things are really tied to the world in which, to the world of experience. Okay, so now quickly I want to go to 6 directions in which I've been persuaded to think, and 6 directions which I think follow if you take seriously this kind of proposal. And so the first thing is a downside of being educable, which is what I have just been emphasizing, is that with only learning and training, which I think are very ancient in evolution on Earth, the behaviors are grounded in experience. They're kind of safe. We've adapted to the world. But if we can absorb instruction from others, then it's very different. So if someone tells us what happened on the other side of the world, we can't rush over to check it out. We just have to believe it or not believe it. Similarly, if someone tells us the outcome of some experiment in physics or biology, we won't rush over to test it. We either believe it or not. But this makes us easy victims of all kinds of false beliefs, ideologies, false beliefs, conspiracy theories. And I don't think that, so in these discussions, often people blame the guys who tell us false things. But here, the emphasis is that there's a fault in ourselves. We have to understand. So the fact that we go around with this great capability to analyze the world, to learn from the world, to analyze the world. We read fiction, fact, we don't care, we can incorporate all kinds of knowledge in our brains, but somehow we can't, it's much harder to test whether something is fact or fiction. So I don't think it's a fault of my model. I don't think it's a fault of evolution. I think there's a basic inherent difficulty that it's very hard to test what's true and what's false. And somehow we live with this imbalance of incredible abilities to absorb information and to run with it, but with no matching ability to evaluate how useful it is and how valid it is. Okay, that's item one. Okay, so item two, popular question, well, if this educability is real, how do I improve my educability? Or often, how do I improve my child's educability? A sub-question is, well, if this thing is real, then there must be a way of testing it. You know, how do you recognize whether someone is more or less educable? So the main point is that the kind of implied test is something very, very simple. The way in which it's, the proposal is very simple, in that most tests test for, you go into the test, and you test it for some previous knowledge, or you test it for some trait. But here, you'll be tested for how you process the knowledge you're given during the test. You'll be given some examples, maybe, how well did you generalize? You're given some text, how well can you understand it and draw conclusions. So the goal of this kind of test is kind of different from most tests. So the only trait this would test for is your trait of being educable. Okay, so it's a different ambition, I think. And of course, whether it can be done well is a matter for future research. But just as a comment, so in a typical IQ test, you may have some question like, if apple is to seed then, well, this wouldn't be an educability test because I'm testing your previous understanding of some relations. I'm not telling you anything new, okay? So I'm not testing you on anything new. And also comprehension tests, they're of the right form. I give you some information, how well can you interpret it? But this is one which came up first from the web. And again, it appears that these tests are designed to test your vocabulary, for example. But that's not the idea. I really want tests which test your ability to learn. Of course, these tests don't have to be a 1-hour test. It's conceivable that the course you give for over a semester is a good educability test. So we have to be broad in how we think about this. Okay, so number 3. So educability has many parameters. So one consequence is that as a mathematical model, there are many parameters, which makes it less elegant, but I think that's the nature of the beast. So even in machine learning, standard machine learning, there are parameters. What's the training data? What's the learning algorithm? Here we've got many more. But just to suggest things which have to be decided, which are parameters, in that there doesn't seem to be some optimal choice in this mind's eye, where you investigate, where you inspect different situations and update them from your learned knowledge. There's some management rules, like how often do you refresh the information, when do you bring something else new. A very important parameter is belief choice, by which I mean that if you're a standalone system, and even if you just learn from examples, or you believe people's theories, how do you decide whom to trust? Okay, so this is an essential part of being a standalone system, which people usually ignore. Although we all know that even in simple machine learning systems, having a carefully composed training data is essential. So, of course, this is something which psychologists have investigated a lot about humans. So we have sophisticated ways of deciding who to believe, parents, non-parents, people on authority, etc., etc. But these are parameters. So there are parameters also for how you combine these concepts and somehow make the learning easier for the learning algorithm. So this is some notion of imagination that, in science, many concepts are conjunctions of two old concepts. And I think it's a very basic part of this kind of cognition, where we can form new concepts by combining as conjunctions old ones. That's a parameter. And certainly a train system will have some reasoning methods in. So for example, expecting it to discover arithmetic or probability theory is probably too much. We can just program that in, just like we humans have been taught these things. So these are parameters, and the main thing to say is that having many parameters is not a bug of this model, I don't think, but it's a feature of cognition. And it also recognizes that we humans are all different. There's no one dimension in which we're all competing in. We've all got different education. As academics, we're specialists in different areas. In this sense, these are like different parameters. It's the nature of the possibilities of being educable. Okay, parameters are there, I think. Okay, so this is going quickly. Singularity. So the idea that computers at some date will become so smart that they'll treat us as animals. So the arguments for this usually start something like this argument of I.J. Good, that let an ultra-intelligent machine be defined as a machine that can far surpass all the intellectual activities of any man, however clever, ... So I'm skeptical of all these arguments. I don't think we should be worried about this. And one way of saying it is that in these arguments, there's always the notion of this idea of ultra-intelligent, something which we can't define, something which we don't understand, something mysterious, something to be feared. But if we define intellectual capabilities in terms of like prosaic, understandable components, like I've tried, there's something much less to fear. Okay, so these machines will do things we understand. Maybe they'll do it faster on a bigger scale, but we'll understand it. And so, for example, it could be that the components I've described are the main components. Maybe that's all there is. But maybe the main point is that what this exercise shows is that there are many parameters to be fixed. There's no one unique ultra-intelligent machine dimension. Okay, just like we're intelligent. Sorry, I shouldn't use the word. Our cognitive capabilities have gone in different directions. We're capable of different things. We're better or worse than each other in different ways. That's going to be the same with machines, and so the machines built will have the same range of parameters. Okay, so this is a brief thing. So studying human behavior is difficult. So in social sciences, the social sciences are different from the physical sciences. Like theories come in different flavors, like different political flavors. Sometimes social science goes what we think is badly wrong, like the eugenicists. They believed in the primacy of genetics, of nature over nurture, more so than we currently do, although in fact some very prominent statisticians were the main practitioners. So what do we have to say about this? Well, so the main problem seems to be that it's very hard to draw conclusions about human behavior that are transferable in time and space. You may do very rigorous experiments on humans, but then if you do the same experiment at a different time and location, you get the same conclusion. I think that's the main problem. So the contribution here is that I've given a word to explanation. So I think the explanation of why this is so difficult is because we are so extremely subject to nurture. Okay, so the ways in which we can change our behavior, change our beliefs is extreme. And this educability notion, I try to spell out exactly the different ways in which we can be influenced by our environment. Okay, so instead of treating nurture as some vague notion, we can actually try to understand, in what ways are we really influenced by our environment. Okay, lastly, and even more briefly, so obviously this is all something to do with education. So I've always felt that education could have a more scientific basis. Of course, many people talk about the science of education, but mostly in terms of doing extensive surveys, trying different methods in the real world and seeing what works best. Certainly very important, but one would think that one should also study the underlying processes which we use when we're educated. So thank you.
Yeah, thank you for the beautiful talk. Let's have some questions now. Yeah.
Thank you so much. I have a very simple question. Do you think so-called robust logic would concern some elements related to behavior, emotions? Thank you.
Well, I think yes, because I think as long as your emotional responses are governed by what your brain does, and your brain naturally chains together things. So something, you may see something from which you predict something, from which you predict something else, which you don't like, is dangerous, and then you're in a state of fear, for example. So certainly, I mean, I think our emotional responses are very much tied in with our cognitive capabilities, and the simple chaining, I think, is fundamental. Yeah, for probably all mammals.
Okay. Second question here.
Hi, I just have a question about your last slide regarding education. So, what are the changes that we should make in theories and practice of education today with regard to educability?
Well, it's a great question, which unfortunately I can't answer. So I think this is more a call for future research. So I think we should investigate how humans learn from this and similar perspectives. I mean, I think the most immediate step of doing research is the one I mentioned about having a test for educability, and the question of whether we can make educability into a notion which people recognize to be a reflection, a useful reflection of some real world thing. Okay, that was the big question: is can we improve the educability of a population by doing something different? And we don't know, and obviously we want to change the educability in some significant way rather than just imperceptible way. So I think that's the first step, which I'd imagine would have to be done before one could go further. But it's a fantastic question.
Thank you. Thank you.
So do non-human animals lack educability, or do we differ from them in degree?
Well, I think we. Well, I'm claiming that it's more than degree. So by the time you add being able to execute a program you're given and being able to represent everything symbolically, I think the combination loses other species. So certainly you can get animals to follow fairly complicated sequences of actions by, you demonstrate some physical contraption. And symbolic naming, I suppose if you've got a dog with a name, it's some sort of very beginnings of a symbolic naming if your dog can recognize it. But the way we can you can give me some instructions, you can tell me some formula in mathematics, and I can interpret your symbolic names and execute your formula. I think that combination is far from other species, to my knowledge.
Yeah.
I was wondering whether the difference between animal and human could not be explained without bringing in the biological component. For example, could it be possible that, well, given enough time, certain animal might catch up to a human being, or at least catch up to a point where we are now in the future?
Well, I think the point is that I think it's hard to imagine our culture without having the biological capabilities which I've described, of being able to share knowledge of this level of complexity, of sharing instructions and formulae, and describe relevant to abstract notions. So I think to get to this our current state of activity, I can't imagine it without having this kind of capability.
Okay. Other questions? Yeah.
Yeah, so I'm not sure about the individual level, but it feels like humanity as a whole works like a big learning machine. And so if you look at the time scales that you put at the beginning of your talk, then it looks a lot like what AlphaGo was doing when he was learning how to play Go by playing against himself. So my question is whether, I mean, from this analogy, you think that AI machines, I mean, learning machines are going to develop conspiracy theories or things like that at some point?
Okay, so I think your first observation, one interpretation is that one could try to analyze our overall culture as one totality. So I was looking at each individual's capability which is needed for this. Okay, but I think you're implying that one could look at the overall culture and see that as something evolving, which is something else one could do in addition. So you're asking whether machines. Well, so my brief answer is listen to Turing. He said that whatever humans can do, machines can do as well. So there's no reason why machines couldn't do that. Whether we want machines to do that, or whether machines will naturally evolve to do that against our will, they're good questions. So I think to those I'd say, we don't want machines to do that, and I don't think machines will naturally do that because they're ill will towards us. So that's the kind of issue which we need to keep under control, I think.
Other questions? Yeah.
Thank you for your talk. I have a question. Can AI lie to us? Or when I ask AI a question, he gave a wrong answer. Can I tell he is making a mistake, or AI is lying to us?
Well, I think for current systems, if the question doesn't make much sense, I mean, it's just running its algorithm. So certainly, I don't think current systems know when they're wrong. Yeah. So I guess again, I mean, okay. So that's the answer about current systems. If you say what's possible in the future, if you try to make something, then again, listen to Turing. You could make a system like that if you wanted to, in any version. There's nothing fundamental against that, but but I think what an AI system is, I think the general parameters of an AI system, so the educability framework gives you some range of parameters for possible AI systems, I think, and they're under some constraints, and I think one of the constraints is that a standalone system will find it hard to find out what's really true in the world if it's just told that. So there are limits to what absolutely a system will know about truth, just like there is for us. Okay.
Other questions? Yeah.
So following on that question, like ChatGPT would make up the references, literature reference, as if they are true, and like which journal, what year, what numbers. Is that this is error at the early stage, or what do you make of that?
Well, yeah, no. I think that's okay. So I try to address that. So one thing I said is that these large language models, all they guarantee is to predict the next word and produce smooth text. You shouldn't listen to what they tell you. You shouldn't listen to the words. If you care more about the words, then you have to invest more in reason, some sort of reasoning. and one could do more. So this robust logic is a way of investing more in the reasoning. So I think there is I think for AI, I think the obvious recommendation is to invest more in making AI trustworthy, in that it should be more reliable, keep facts straight. But it's so basically, I think what happens with these large language models is that they read all this text, and they just don't learn many of the relations in there. So they don't actually learn which paper was published in which journal, but somehow from some averaging they make something up. Okay, so they just never went in the system, the truth about that relationship.
Okay, last question. Yeah.
Yes. Do you believe that a framework like Educability can help the state of studies in the social and political sciences that are nowadays of the Aristotelian tradition of verifying axioms, coming up with theories that have certain soundness, and things like this? I'm not trying to put you in a bad political spot, but since you came up with this framework, can it be used to really venture into these, let's say, social sciences and tell them, you come up with something that you call theory, quote unquote, but it lacks the Aristotelian characteristics of theory, and implications are for policymakers?
Yeah, so thank you for the question. So in some sense, I'm hoping the answer is yes, because in social science theories, surely you have to understand what the human is, or what his behavior is. So this is one kind of description of what human behavior is. And if it's an accurate description, a useful description, then surely it should influence social sciences. That when we just people said for thousands of years that the important thing is to understand ourselves, but in a remarkable way we haven't really started. And yeah, so my answer is I hope yes. That's my answer.
Okay. Well, we conclude this part of the conference for the speeches given by our 6 great rewardees. I'm grateful to all of them. I should mention that people on the street were saying that we are running a great conference with the greatest mind in here. So I'm happy that it's already propagated to the whole country. And I wish that next year we have the similar 6 awardees as powerful as today's. Thank you very much for the great talk. Thanks.